inside that. Okay, so that you can and if graph, if you have been given a simple graph, you can directly say that. Let's, for example, I'm giving you two graphs, G1 and G2. You have to tell me which of the following is a DAG. So this is A. Okay, can you tell me which of the following is a DAG? Is G1
G1
a DAG?
Yes, sir.
Yeah, this is a DAG. Yes, this is not a DAG. You can see that.
BCD, homocycle.
Which one? B?
BCDB, homocycle.
Yeah, B, C, and D. This one, DB. This is a cycle. This is okay. That's why it's not a DAG. Okay, so this is simple. This is pretty simple. And if you have been so this was a very simple graph. So you can directly say that. If you have been given a bit complex one, you have to calculate, maybe write a topological sequence. So, like, you can do the topological sorting, and if you are able to do that, you can say that this is not a cyclic graph, or this is a DAG graph. Okay, you can directly say that. So we'll just talk about how do you do the topological sorting. So this is also very simple. Okay, so it's just that in this sorting, you basically write a sequence, right? You write a sequence of vertex, and you write in such a way that the later vertex, okay, you write in such a way that the later vertex that you're writing, okay, is somewhat dependent, okay, on the earlier vertex. Okay, so if it is, and the step that you follow to write a topological sorting, this is also very simple. I'll just give you an example. How do you write the step? You can write it as, the first step that you follow is, it's a simple one. If you just iterate it, this is the first step. In the first step, what do? You basically calculate the n degree for each of the vertices, right? Each of the vertices of the plot, whatever the plot has been given to you. If you have to write the topological, if you have to do the topological sorting or write the sequence of that, the first step should be to calculate all the n degree of the vertex. Okay, and then what do? You have to just select a vertices with n degree 0, correct? You have to pick the vertex which has n degree equals to 0, correct? And that vertex, whichever vertex that you have selected where the n degree is 0, you just add it to your sequence. Add it to the sequence. Okay, the third step is, and again, wherever you have find it, so you have now wherever the n degree was 0, now you have already added it to the sequence. Now you can remove that vertices, plus you can just remove the edges that is connected to that vertices. Okay, so now you have to remove all that vertex. You have to remove, let's, for example, the vertex was I, that you have to remove the vertex and all the edges that was connected to it. or you can say the okay. So now you have done the first step was you have calculated the in degree wherever it was a 0, you just add it to the sequence and you have removed that vertices. Okay. And then after removing the vertices, you have removed the connection also. Wherever it was incidenting, you have to remove the edges also. Now the fourth step is you just update the value. You update the value, update the value of in degree. Okay, of the remaining vertices. Whatever is remaining vertex. And the fifth step is you have to repeat it. Okay, so from here to here, repeat this. Let's for example, the same example that we were dealing. Let's for example, this we'll try to do that. We'll try to write the topological sorting for this. Let's for example, this starts with 0, and then you have 1, you have 2, okay. Now, first of all, tell me, is it a DAG?
Sir, instead of 0, 1, 2, 3, 4, can we take A, B, C, D, E? That will be easier to, because we will be dealing with numbers.
Correct, correct. Is it a DAG?
Yes. Yes, sir.
Yes. Or you can do the topological sorting also. Now let's start. What was the first step? What did I say? You have to calculate the in degree for all the vertices. Can you calculate the in degree? What's the in degree for each of the vertices? Can you tell me the in degree for A?
One.
Ones.
1. Similarly, what is for B? It is 2. For
2.
C?
0.
0. What is for D?
2.
And for E, it is 1. Correct? Yeah.
Yes.
So the first step was we have done the first step. We are done with first step. The second step is to pick the vertices with the in degree 0. Now select the vertices with in degree 0. Which of the vertices are the in degree 0?
C.
The C. Correct. So you can write that your topological sorting. So C. You start with C. Now what is the next step? What is the next step I told you?
Remove it and its edge.
Yeah. Remove that. So we'll remove that. Okay. So now I'll remove that. So I'll remove this C. And also the edges that are connected to C. Correct. So I'll just remove this also. Okay. Now after removing that, we have to update that. After removing, we have removed that. We have added to the topological sorting, or like the sequence that we were writing. Okay. And now we have to update the value of the in degree again. Now we will have to update the values. What is the updated value of B?
B remains same,
right?
2.
Yeah.
Yeah. What should be the value of A? It will be 0, right?
0.
0. This will be 1. This will be 2. Okay. So whichever was the connected vertices, right? The incident, like from the C, whichever vertices which was incident from the C, only those vertices in degree will get impacted. Okay. So you can see that A got impacted. Other than that, none of the vertices got impacted. Now you can see that. Now you can remove A, right? You can remove that A and you can write it here. C, after that you have A, correct? And now you can remove this. I'll just remove it in the same plot. So I'll just remove this. A.
So what does incident means? Incident means connected, is it?
Connected from that vertices. Yeah.
Okay.
So I'll just remove A. And after removing A, what should I remove? All these vertices, all these edges also.
Yes.
Okay. After that, I'll update the values. So all these values will be updated. Correct?
Right.
What is the in degree of this? 1, in degree 1, and this is 0. Correct? After that, I can write it. So E is having the in degree 0. So I can write it here, E. Right? And now I can delete this also. After that, again, I'll update the value of in degree. So here, again, in degree will be 1 because it was not impacted. D was impacted. So here it will be 0. So now I can write it here, D. And after that, the B will come. Correct? So this is pretty simple. The topological, how do you do the sorting? Okay. And you can see that whichever was the later vertices, there are some like the A was somewhat dependent on C. Similarly, E was dependent on A. D was dependent on E, and B was dependent on D. So that is how. So that's why topological sorting helps you to calculate the longest path also, right? So now the next part that we'll be dealing is how do you calculate the longest path in a DAG. So till now we have done the one thing. We have just sorted it. Okay, so we've sorted it. Now we'll calculate what's the longest path, okay, from any, like let's for example, we will start from the C itself. In the same plot, we'll start with the C. Now we'll see that from C, what's the longest path from each of the other vertices. Okay, now let's deal with that. So till now, is it clear to everyone? So the first thing that we have discussed is the DAG. That was pretty simple. How do you know about the DAG? So directed acyclic graph. Whatever figure has been given to you, you can just think of these 2-3 properties. Okay. Yeah. Go ahead. Are you asking something?
So for a DAG, there should be at least one vertex with in degree 0.
Correct. One in degree, at least one. There can be more, but at least there should be one. And there should be a out degree, like a vertices with the out degree also 0. Okay. And there should not be any cycle. Okay. These are the 3-4 properties that you should be checking in the DAG. Is it clear? See, even now, and one more thing in the DAG, whenever you are removing one edge, like you have removed the, so not edge, one vertices. After removing one vertices, you can see that after that also, so we have removed the vertices, one vertices we have removed. And after that also, you'll see that the next step also you'll be getting a DAG only, like a cyclic plot only you'll be getting. Okay. Whenever you are removing a vertices, after the first step was what? We just calculated the in degree, and after that we remove we generally remove that vertices with the in degree 0 along with the edge, incident edges or the connected edges we remove. After that also you'll see that you'll get a DAG only. That is also one of the properties of a DAG. After we'll remove the vertices that has in degree DAG in the corresponding edge on the edges that is connected. In the result also you'll be getting a DAG itself. Okay, is it clear? Let's go to the let's deal with the sorting now. Not sorting, we have done it. So let's calculate the longest path in a DAG. It will help you to find the longest path in a DAG from a given source vertex to a destination vertices. Let's deal with the same example. Okay. Yeah, this is important. You can just have you can just concentrate here to calculate the longest part. You can get some simple problem from here also. Okay. And I already told you this whole week is very important. 50% of the final exam paper will be almost 50%, 40 to 45% will be from the last 2 weeks. Okay. So whatever the paper, out of this 15, 16 problem that we'll be having approximately 6 to 7 questions only from the graph theory. But those are simple, not that difficult. But yeah, you should be knowing all the concepts. If you are knowing the concepts, all the concepts will be able to solve. There is no any difficult graph has been given, any big graph with more than 6-7 vertices has been given. All the graphs will be having less than 6-7 vertices only. Okay, now calculate. The next part is how do you calculate the longest path in a DAG. So I'll just write the steps that you have to follow. Okay, that you should be having in your mind. So the first step that you calculate, the same thing you will be doing. Whatever the sorting we have done. So half of the part is we have already learned. Okay, so now let's start. So again, you have to compute. So calculate the in degree first. Okay, for all the vertices that you have of your DAG. Okay, now what was the second step in the sorting? Can you tell me what did we do after calculating the in degree for all the vertices? What have we done in the second step? What?
Just remove the vertex of in degree 0.
Correct. So there we were removing the vertices. Okay, the vertice itself where the in degree was used. Here there is one new concept that will be added. Correct. Yeah. So here it will be just the longest path. So here we'll be just initializing the longest path to that I. Okay, like to I, like you'll be just initializing the longest path to all the vertices. Okay. So we'll just
initialize to 0 to all vertices.
Correct. All the vertices that you were having, you just have to initialize the longest path to each of the vertices as 0. Now you can say that to reach each of the vertices, I don't know how to reach that. Like that's why we are just initializing longest path to each of the vertices as 0. Okay. Now the third step is, so the first thing that you have done is you have just calculated the in degree for each of the vertices. Then you have just calculate the in degree. So two things you have to calculate it now here. So first thing is you have to calculate the in degree, and then you have to initialize the longest path to each of the vertices as 0. Okay, so I'll write the algorithm, then we'll solve some problem. There you'll be having a very clear picture of that. Okay. So the first thing.
Sir.
Yeah.
Sir, I have not yet joined this course. How can I join? Because in my dashboard there will no link.
Not join the course. Course means
This course.
Okay, this course. Okay, you haven't. Okay.
And in my dashboard it is not showing this course link.
Okay. Yeah. So maybe you can wait, or anyone else is having this issue? Okay. No.
Actually,
So we don't have.
most of
You
us.
can tell Piyush Virale, sir. CT coordinator.
Okay. See, what you can do is you can just mail me regarding that. After that, you'll get the that information. Okay. So you don't have to worry about that. You can just mail me. I'll just forward it to the
How can I mail you, sir?
Yeah, I'll just write my mail ID in the chat box itself. Okay.
Okay.
Not a big issue. It will be done. So don't worry about that. No one else is having this issue, right?
No, sir.
So most of us
Sir, I
don't
have
have
some
a
doubt.
current idea.
I don't know where to find the link for this one.
You will be invited.
Yeah. The invitation, you would have got the invitation regarding.
No, sir, I didn't get. I didn't get any.
Okay, so if you haven't, you can just mail me regarding that. I'll just, it'll be most probably you'll be getting sometime. Okay, so we'll just add it to the discourse. Like I'll be sending you the invitation. Then after you can just join it there. Okay, so I've just mailed it there.
Okay, sir. Sir, I have some doubt in graded 10. Can I ask in the last of the session?
Yeah, you can ask at the end of the session. Okay.
Okay, sir. Okay.
Or maybe you can ask it in the TA session. TA session, I guess, I don't know when is that. Maybe tomorrow we'll be having, I guess, 10 to 12.
Okay, sir.
Okay. I've just mailed, I've written the mail ID. You can just check it out. Anyone who's having any issue, you can just check it out. Now let's deal how to calculate the longest path in a DAG. So we were just discussing that if you have been given a directed acyclic graph, the first step that you do is to calculate the in degree for each of the vertices. Then you just initialize which longest path to each of the vertices as 0. Okay. So because till now we don't know how to reach any of the vertices, so that's why we have just initialized it to 0. Okay. Now the third step is just have to find a vertices with the degree 0, whatever the vertices that has the degree 0, we have to remove it. Whatever you were doing in the topological sorting, you just remove it, and then you have to add that vertices in the topological sorting, and you have to give the longest path. So whatever the longest path has been assigned till now to that vertices, okay, you just write it there itself. With the topological sequence, you will write the longest path to that individual vertices also. Okay, let's for example, maybe if you're not able to understand it after writing the whole algorithm or the the algorithm, I'll just take an example. After that, it will be clear to you. So now we have to find that vertices itself. You have to find that vertices u with degree equals to 0. Okay, and then you have to remove that vertices. Remove it means this u from DAG and add this to your topological sorting, and also give the longest path whatever has been assigned till now. So it was in the first step, it will be assigned always 0, because if you are starting from a vertices and if you are asking what's the longest path to reach that vertices itself, it will always be 0, right? So that's why we'll be assigning 0 to that vertices from where we are starting. So give longest path to 2. So that will be basically 0 in the starting. Now the third step is what? So we have done it. So all these three, not the second one, but the first and the third was already there in the topological sorting also. Now the fourth step is to update the value. So that was also there here also, like in the topological sorting also. So you just update the values, of in degree for all the remaining vertices that you are having. Basically, those are adjacent. I already told you the only the adjacent vertices, the vertices that were connected, okay, will get impacted. The integrity for those vertices will get impacted. Other vertices will be having almost the same, like the same integrity that was there in the starting. Okay, so adjacent to vertex u. Now till now we have done the same thing as we were doing in the topological sorting. Now the fifth step that we have to do is, now we have to update the value of longest path to I. So this is the new step that we are doing. Update the, I'll write the longest path to that point. Okay, whatever the point, let's for example, this is I, right? We were discussing. So longest path to that topology, like the longest path to I, update, we have to update those values. Okay, and I's are what? I are the vertices that are connected or adjacent, right? To you. Okay. Now you have to, and the formula that we'll be using is longest path to that I will be using as max of LPT I, or longest path to that U that we were having, right? U plus 1. Whatever the maximum value that will be getting, that you have to update it. Okay. And now the sixth thing is you have to repeat it. So you have to repeat this whole step. Repeat this. Okay, let's deal with that. So the whatever the step that I've told, okay, if you didn't get that, maybe after the example you'll be able to understand it. Okay, let's deal with the same example. Okay. Now The first iteration, our first iteration, you can say that. Okay, let's first tell me what is the first step. What is the first step?
Calculate degrees.
Okay, so these are the in degree that we have calculated. This is the first step that we have calculated. What is the second step?
Initialize all zeros.
Initialize longest path to 0 for all vertices.
So, can you tell me the in degree that I have calculated is correct? Okay, I guess this is correct, right? Yeah, this is correct.
Yes.
This is the first step has been done.
Yes.
Now the second step. This the second step is to initialize the value. So I'll always be giving the longest path to that particular point in the blue, okay, green color. So yellow is for the in degree, and green I'll be giving it to the that we have initialized the longest path to that particular vertices. Let's, for example, we have initialized to 0 for each of the vertices. Okay, so blue I'll be writing LPT, and yellow is to the in degree. So this is the second step. It is done. What is the third step? You have to find the vertices U with the in degree 0. What is the vertices? We are starting from here. Starting point for us is this. Okay, we have started from here, so we'll add it in the topological sorting. So the third step was you have to find that U with the in degree 0 and remove it from the DAG. Now you have to remove this, so and add this to the what was that? Your topological sorting itself. Okay, so the first thing is you have to identify those vertices with in degree 0. Okay, that we have identified, that is C. Okay, now update the in degree for all the. So after this, so this topological sorting, you got this C, the first step. Now the fourth step, now you can see that the fourth step is after finding the U, you have to update the value of in degree for all the remaining vertices. Okay, let's see. So whatever was the let's remove this. Okay, what's the in degree? Updated, we have to update the value of the in degree after removing that. What is the in degree? This will get impacted only, right? So this will be 0.
Yes.
Yeah, correct. So this will be 0 only. Okay. I guess we did. I just added this line also. So this will also got removed. But the in degree for earlier it was 2. Now it is correct. So the in degrees. So the in degrees are correct. Correct. For each of the data point, it is correct.
Yes, sir.
So we have done. We are done with the fourth step also. Update the in degree for all the vertices that are adjacent to the vertices U. Okay. Now the fifth step is what? Update the LPT, longest path to that particular vertices. Correct?
Yes.
Yeah. See, if I'll just repeat it again, if you are getting confused. See, so I guess the first step is pretty simple. The second is also simple. The third step, you just have to see that you have to find that vertices with the in degree 0, and then you have to remove it from the DAG. Okay, and you have to remove it from the DAG, and you have to add it in the topological sorting that you are writing it here, and then you have to update the some other values also. That is the longest path to that particular U. So the longest path to this U is what? 0. Because it was 0, right? In the starting, it was 0. Now you can see that also, if you have to reach C, how will you reach? If you are starting from C itself, so what's the longest path? It's 0 only, correct? It's not it.
Yes. Yes.
Yeah. Now the next part is, now you are updating the value. You are updating the in degree for all the vertices that are remaining or that are adjacent to this vertices C. Correct? So now you can see that. And I already told you, right? So whichever the vertices that are adjacent, you have to do something else also. You have to update the values of the in degree for all the remaining vertices. That is fine. And then you have to update the value LPT of I. And I is what? The adjacent vertices for the earlier. Like, so we have done it for the C, right? So we have done it for the C. Now for this C vertices, let's for example, this for U, this is U is C. What is the I for this? See, you can see here.
A and E.
You have to
A and E, yeah.
Yeah, correct.
A and E.
A and E is the, yeah, correct. A and E. Right? Now you have to update this. Update, what you have to update? So you can see the fifth step. You have to update for the longest path to, yeah, correct. So you have to update the longest LPT for A. What should be the value? I told you maximum of LPT to A or 1 plus LPT to, what was the U? C, right?
C, right.
Is this clear to or not? Yeah. Is this clear to everyone?
Yes.
Till now? So now you can see that what is the maximum? You can see that maximum of, what is this LPT to A? What is the longest path to
0.
A now? 0, right? Correct, 0. And what is this? 1 plus LPT to C?
1.
That is also 0, right? That is
1
0,
plus
right?
0. Yeah,
1 plus 0. Correct. So this would be maximum of 0, 1. So this is 1. Right? Similarly, we have to calculate for this, we have calculated. Now we have to calculate for E. Let's calculate for E. LPT for E is what? Maximum of LPT to E, comma, LPT of, what was that value? C, right? C plus 1.
C plus 1.
Again, this is maximum of 0, 1. This is 1. Right?
Can you?
Is it clear to
can you
everyone?
tell me-
So now we are done with the, yeah. Yeah, go
Can
ahead.
you
Go
tell me
ahead.
why we are going with max of this thing? Will there be a scenario wherein we will have LPT to E, which is greater than LPT to C plus 1?
LPT, okay. You're asking, see, this is the first step that we are doing. So LPT of E now is 1, but it will get updated later also. See,
Right.
yeah, it will get updated because we are not adding that E in the topological sorting. So we have done for the C. Next time, what we'll be putting in the topological sorting? The next, where the vertices are, where with the vertices as in degree 0, right? So the next part is what? After C, what is the next that we'll be updating? See, all those things that we are updating, this is just the part of the initial, like we have initialized with 0, but see, from here also you can see that LPT that we have got, longest path to E that we have got is what? 1, right? Now we have got 1, but this is not the correct. So you can see that from C, if you have to start from C, if you have to go to E, you can get this path as the longest path, C to A and A to C, A to E, right? But this is not the updated version. This is not the final. See, the final only we have got it for C only. The next step that we'll be getting for the next part. Okay. Are you getting my point? See, yeah, for A, you can see that longest path to A from C. What is the longest path to A from C? Is 1, correct? 1. So from C to A directly. But for this, we have got it, right? For this, we have got it. And now after, we'll see that in the next iteration also, we'll just update the value of the A as 1 only, because the next thing that we'll be getting with the in degree 0 is itself A. Are you getting me?
Okay.
Yeah. See the next step. Yeah, next step, we'll start with the next step now. So we have updated LPT of E and the A. What should be the next thing? Now we have to take this thing. We have removed all those things. Now we have updated the value of A. Now you can see that I'll have to take it again. Now we have done with the first part. Now the second part is we have to find that vertices with the in degree 0. So now we have found this correct? We have founded this. After this, what we have to do? The next step is what? We have to remove this A, correct?
Right.
Yeah, and one more thing. So we have to keep updating the value of the LPT also. So for C, we have got 0. For A, what is the value we have got? Right, 1. For E also, we have got 1. For this, all things, we are having a 0 only. Right?
Yes.
Is this clear to everyone? What is the green that we are writing? Now the next step is the second iteration that we'll be doing. We'll be removing this A now from here. After removing this A, we'll be removing all those A's also. We'll remove this. And after removing this, what is the next step? We'll be adding it in the sorting. After this, TS. After this, what was that? C, right? The first step. And after that, we have got A. And LPT to C is what? 0. And for A, what is this? A is 1, correct? Or not? A is worth 1, right? So we have written 1. We didn't write it for E because E will get updated further. Because we have not written in the, so this is the final that we are getting now in the topological sorting that we are writing it. So A1, this for C we have got 0, and for A we have got 1. So that means what? If you have to reach A from C, you'll be having only this path, C to A directly, okay, with length 1, because it's a non-weighted graph. Now let's see here. We have removed A, C, everything. Now update the value. Update the value of the incoming in degree. What should be getting? We'll be getting what? Here it will be 1, correct?
Yeah.
What will be getting here?
E will become 2.
E will be 0, right?
0 in degree.
In degree, yeah, in degree, sorry, yes.
In degree, you'll be getting, here it will be 1, here it will be 0, here it will be 1, correct?
1.
Now, for this step, our U was what? Vertices with in degree was what?
A.
What is I for this case? What was the incident? What was the related? See, you can see
E, D, and B.
Which are the vertices that were related to A?
E, D, and B.
D, B. Now you can see that E, D, and B. Now you have to calculate the LPT. So longest path to E. What should be the value of longest path to E? Maximum of longest path to E is what? 1. Correct? Plus 1 plus LPT of, what was that? A, right?
Yeah.
What should be the value now? Maximum of
1, 2.
1, 2. So you'll be having, correct? So now we have got the LPT for E as 2. So you will update the value of longest path to E. Now similarly, you'll calculate for LPT of what? D. What should be the value you'll be getting? Maximum of
0,
LPT of D, 1 plus 2 LPT. Yeah. So it will be what? This is A, right? This is A. So this will be maximum of
0, 2.
What is that? 1, 0. This is LPT of D is 0, right?
Yeah, 0,
yeah. Yeah, this will be 0, 2. So you'll be having 2. Similarly, you'll be calculating the longest path to, what is that remaining is B. This is maximum of, what should be the value? LPT for B is what? 0, 2. So you'll be having 2. Okay, so now we are done with this step. What is the next step that we'll be doing? Now we have updated the value of longest path to each of the cases, correct? Right? And now we'll be searching for those vertices where the in degree is 0. Now, what is that? Now I'll copy it here. The next step, okay, I'll write it here itself. The next step is I'll be just searching for that vertices where the in degree is 0. So next step is E. E is having a in degree 0. So I'll be just searching this. I'll be taking this and I'll be putting this in the here. What is the longest path to E? The updated version of E is what? 2, right? So I'll be writing it here 2. Okay, I'll delete this. I'll delete this and this also. Now I'll update the value of in degree. The updated value of in degree here is 0. So here we'll be getting 0 and here it will be 1. Correct? Now I'll have to update. So now for this case, my U will be E, but I is D. Correct? Now I have to update the value of LPT. So LPT of D, I have to update. That will be maximum of LPT of
2,
D, 1 plus LPT of E. So this is basically maximum of 2, 3.
2, 1 plus
right?
2.
This is what. So this is 3. Okay. Yeah. Now we have a D is having an in degree 0. So I'll update it here. D is here. And now I'll write the longest path to D is 3. Similarly, now we are left with only B, so I'll be writing it here. And now you can calculate the LPT for B also. So that will be, I guess, the 4. So this is the, so now from the original plot, you can see that if you have to reach it from C to A, where is the original? Yeah, so this is the original one. I'll just copy it here. I'll show you. Now our topological sorting is also here. This is T. CA EDB, and the longest path to that I is also 0, 1, 2, 3, 0, 1, 2, 3, 4. Now you can see that if you have to reach it from C to A, you can see that there is a only because we are starting from C, right? The longest path from C to A is what? This CA only, right? If you have to reach it from E, right? If you have to reach it to E, if you have to go from C to E, what's the longest path? You'll be having what? CA and AE, right? Yeah, CA, AE, correct? And that's the longest path if you have to reach it to E from C. Similarly, for D, you can see that what's the longest path that you have. You will be having 3 edges, like with length 3, as this is a non-weighted graph. So you'll be having from C to D. How will you reach from C to D if you have to reach it?
C to A to E to D.
Yeah, CA, A.
E,
No, that's not
ED.
the longest. Yeah, CA, AE, and then ED. That will be okay. That ED, yeah. And similarly for E also, you can find the path. How will you reach it from C to B? That will be having a length of 4. Okay. So this is how you do the topological sorting, and this is how you calculate the longest path. Is this clear to
Yes, sir,
everyone?
yes, sir. But what I'm asking is, if you scroll up a little, when we are calculating the longest path, we are looking at max of, say for instance, this LPT of E. We are looking at max of 1, 1 plus LPT of A, right?
Yeah.
Now, in all our cases, we only went with the value on the right side, not on the left.
Yeah, that's the correct. But yeah, so the plot was like that every time, because see, you'll be having the formula is what you have maximum of longest max of LPT of whatever the vertices that was there available,
Right.
comma 1 plus LPT of
LPT
this
of
U.
1 plus U.
Right? There can be some problem. Yeah, 1 plus U. You can have a, let's for example, this U are having only 1 plus 0, and this was 2, right? So maybe so for some case, you can get this value.
I'm not able to think of that.
Did you get
case,
the idea?
Yeah, I get that idea.
That depends on the example. Yeah, that depends on the example that you'll be getting. Yeah, but you must be getting for some graph, right? Otherwise, the formula would have been 1 plus longest path to U itself.
Right. Okay. Thanks.
Because many a times you'll be getting, even though your plot is like A, B, C, D, but you'll not be always be getting 1, 2, 3, 4 only. Maybe there can be a possibility that you'll be getting 1, 2, 2, 3. That's it. Okay, because there can be a path, right? If you have to reach it from A to B, there is not a direct path. We'll have to go through we'll have to hop, right? So that we'll be having 2 edges, right? So there can be some example like this also. Is this clear to everyone?
Sir, can you explain this LPT, how to find that max?
Okay, I'll explain you. Yeah. So what I was saying is, see, so are you clear with the first starting steps and all? I'll repeat it again, everything. I'll just make it long story short. Okay. So I'll just, what I was saying is, the first step is to calculate the same thing that you were doing for the topological sorting. You have to do it. Calculate the in degree first of all. And then the only thing that you have to do is initialize the longest path to 0 each of the data points, so that because see if I'm starting from C, if I have to reach C here, I'll have there is no path to reach C, right? Correct? Is there any path to reach C? No. Right? So we have initialized the longest path to, like, because we are starting with C and we have initialized everything with 0 as of now. The next step that we'll be doing is the next step that we'll be doing is we'll be just writing that C itself in the topological sequence that we were writing earlier also. Okay, so we'll write the sequence in the topological sorting where we were writing the sequence, right? So we have written here C. Okay, what is this? C. Okay, and then we have updated the value of longest path to C is 0 because we already know that you can't reach it to C. So that's why 0 is updated. Now the next step is you have to remove this C. So we have removed this C and all the edges that is connected to C. Okay, so now we have removed C plus all the edges that is connected. Now you can see that the plot came here, right? Now we'll update the in degree for all the other cases. That was basically you have to update for all those vertices which were connected to the earlier vertex, that was basically C. Okay, we have updated the value. Now you can see that you are left with A. Okay, A is basically what? A is basically the vertices with in degree 0. Correct? The most important part that we were doing is the fifth step. Okay, the fifth step is till fourth step. It is simple. The first step is in degree, and then the second is longest, initialize the longest path. Third degree is just write the vertices with the in degree 0 in the topological sequence and update the value of the longest path. The longest path is 0 itself in the starting. But the fourth step is you have to remove that C and all the edges connected to that. Okay, and update the value of the in degree. Now the fifth step is the most important, where you have to update the value of the longest path to I. What is that I? All the edges that are connected to the previous vertices. For C, what are the vertices that are connected? This A, so incident vertice A and E, correct? A and E. So that means you have to update the value of longest path to A and E, right? Because from C you can go to A and E only, right? So you have to update the value of A and E. So those I'll update it. Now the formula for that is, so if I have to update the longest path to A, that is basically maximum of longest path to A plus comma 1 plus longest path to C. C is the earlier vertices where the in degree was 0, right? So for this case it was 0, right? So it's 1 plus 0 and the longest path to A is already 0 because we have initialized the value as 0 itself. So now 0 comma 1, the maximum of 0 comma 1 is 1. So now we got the longest path to A as 1. Similarly, so we'll update the value as 1. And similarly for E will be 1. Similarly, you can see that longest path to E is longest path to E, comma 1 plus longest path to C. C is basically the earlier vertices where the in degree was 0. You got the value as 1. You can see it from here also. This is the original block. Now, if you have to reach to A, you can see that you can reach it from C to A. Right? The longest path to C, A is what? 1 only. But for E, if you are claiming that for E we have got 1, but that is not correct, because when you will be updating the topological sequence, right? So the next step that you'll be doing is after C we'll be putting A. For A we have got the 1, is that is fine, fine. But for C it will get update again. So that's why we'll be getting the longest path to E as 2. Is this clear or not?
So then in second step, LPTA, then we have to updated A value or previous LPT of A, sir.
So here we have updated the value of LPT of A, correct?
Yes, sir.
So this A, C, here has been mentioned. If you just go through the steps itself, see, I've written all the steps. First step, so see, after you will get the vertices with in degree 0, just put it in the topological sequence and write it as 0 itself. The fourth step is update the value of the in degree of the remaining. So we have updated the value of the remaining. Now we'll have to update the value of the in degree. And now the fifth step is the most important. Update the value of the LPT of I. I is what? I told you, right? See, I, E, R, this I are the vertices that are adjacent to U. And U was what? Where the in degree was 0. Whatever we have removed. So in this we have removed C, correct? And
Yes,
what is
sir.
connected to C is A and E. So
And
that's
E.
why we have to update the value of A and C, E, right? Correct? And
Yes.
now we have updated the value of A and E. Now next step is we have to search for that vertices where the integrity is 0. Now we have seen that A is that vertices. What is the connected incident vertices for A? A is for E, D, and B. So next step will be updating the value for E, D, and B, all the three. You can see that. Next time we'll update the value of E, B, D, all the three vertices, right? Is this clear?
Yes, sir.
Yeah, you can go through this. I'll just share this slide, like whatever I'm writing, because this week is tedious, so you can just, that's why I'm writing each and everything clearly, so that you can just go through this slide once again. Okay, I'll just share it in the end, so that you'll just go through this slide. Okay, even though it will just go through this slide, and I will be solving some problem in maybe in the next, I'll take one more session for this week. We'll solve some problem, 10-15 problems. Most probably you'll be able to solve it in the exam also, the problem. If you are will be attentive in those sessions, most probably you'll be solving in the exam also. We'll just solve some problems similar to the paper, similar to the graded assignment, practice assignment, and that you can expect the similar questions in the exam also of the same difficulty level. Is this clear to everyone till now? Is it clear to everyone?
Yes,
Can
sir.
we move to the next topic?
Yes, sir.
Can we move to the transitive closure?
Yes, sir. Yes.
Okay. Yeah. So the next thing is transitive. What do you mean by this transitive closure? See, whenever you make a transitive closure graph, right? TZ, what is do you call TCC? That means, so for any graph that has been given to you, right? So this graph will tell you, this graph itself, if you are able to plot this transitive closure graph, that will directly tell you how can you reach it from one point to another. Okay, that directly it will be showing you. Let's, for example, so this I'll just write it in whatever I have said in a graph G. If I'm giving you a graph G, if there is a path, any path from vertex U to any vertices other vertex V. So from U to V in a graph G, if there is any path from vertex U to Z, then we'll add in the TZ graph, like TCC, whatever we have plotted, we'll add a direct graph. We'll be adding a direct is from the vertex U to vertex V for all this UV that is belonging to the original vertex. See, what did I write here? You have been given a graph, okay? If there is a path from U to V, any path, like that means from U to V that is crossing three edges and then reaching V. Okay, so what I'll be doing in the transitive closure, I can draw a direct edge from U to B, so that in the TCC graph, whenever I'll be denoting, you can directly see that, okay, I can reach it from here to here. I don't know how many hop I'll be doing, but I can reach it from this place to that place. Okay. See, and then if you are adding, after adding all the direct edges, whatever the plot you'll be getting, the newly formed graph TCG that you call is basically called as transitive closure of the graph G. So you're having a graph. Now, which type of problem you can expect from this? This is what, like, which type of problem you can expect from this topic? Okay. See, I'll be giving you one question. So have you understood this concept? This is pretty simple, right? any graph that has been given to you, if you are able to reach it from A to B, I don't know how many hopping you are doing. Hopping means how many edges you are crossing. That doesn't matter. In the TCG graph, in the final graph that you are making, that is the transitive closure graph that you are making, you can directly plot the direct connection. You can give it there. Okay. See, if you have Z, and I'll be making TCZ here. If you have a graph Z, and that graph is A to B okay, can somebody tell me in the transitive closure graph that I'll be making, how many extra edges that I'll be making? How many extra edges I'll be making? Can you tell me? How many?
N or N minus?
No, see. Okay, so see.
One, sir.
One.
One
A to
or
B, B to then A to C. Closer, transitive closure. So,
one or two?
This is one. We can add between A and C one. And then where are we going? We are not going. Okay. We three, sir.
Three. Which are those three?
A to C, D to C, and D to A.
A to C or C to A? Sorry. C to A. No, sorry. You are correct.
A to C, sir.
A to C, one.
And then D to C.
Yeah, B to C is also correct. B to C. I guess
No,
two only.
No, D to C, sir. D to C.
Okay, the other is D to C.
D to C. Because D to B and B to C is possible, right? So
D to B and B to C. Yeah, you can reach
and then
it. So
D to A. Then D to A.
D to A you can reach? I don't think so. You can reach it from D to A.
D to B, B to C, C to A.
Correct. You can reach it from here to here also. Yeah.
So those three.
Anything else? Anything else that you can make it? You can think of? I guess three only. Now can you do it for this plot? How many you'll be adding for this plot? How many have you added for this plot? I'm giving you the options. Option A, B, C, D. So 4, 5, 3, 6. Take your time. Try to give me the answer, correct answer. Okay, I'll make it simple. Now tell me. C to B. Can I do C to B?
Yes, sir.
Can I read?
That is one.
One. Okay, one. The second is, can I make C to D?
Yeah, C to D.
C to D also I can make it. Can I make it from C to E?
C2.
C to E. Can I reach it from C to E?
Yes, sir. Yes, sir.
Okay. Okay. What's the next? Can I reach it from E to B? Can I reach it from E to
Yeah.
B?
Sir.
Okay. Anything else? Anything else that you can think of? Anything else that you can think of? I guess no, right? So I guess the fourth is correct. I don't know.
A to D, sir. A to D.
A to D. There is already a connection.
Oh, there is already one. There is already.
2,
Yeah.
3, 4, 6.
Yes, 4.
4, right? Anyone is having any issue in this? This is pretty simple, right? Anyone is having any issue in this? Understanding this? Anyone is no? Okay, let's
Got it,
move to
sir.
the matrix. Yeah, matrix multiplication then. The fourth topic of the day is matrix multiplication. See, you already know the adjacency matrix, right? What does this tells us? Adjacency matrix. Have you read about this adjacency matrix?
Yes, it tells from which node you can go to which other node. It is indicated by 1 if there is a path direct edge between from one vertex to the other.
Correct. So this matrix you can directly write it, right? So I'll just, for a simple plot, A what should be the adjacency matrix? What should be the value here? 0.
0, 1,
Okay,
0, 0.
0, 1,
0, 1,
0.
0, 0.
I guess no, this is 1, right? A to C, there is a connection, right?
Oh, A to C is 1. Yes, A to C is 1. 0, 1, 1, 0.
Okay. A to D, there is no connection. B to A, what is the value? B to A
1
is 1, right? B to A is 1 because undirected graph, that means you can represent it like this. This is same.
Yeah.
So, and B to B is 0.
0.
This will be 0, 0. B to C
0.
is no.
0 and 1.
B to D is 1. Okay. C to A is 1.
1.
C to A is 1,
0.
right? C to A you can reach it. C to
1.
B is 0. 0, 0, and this is 1. Similarly, if for this DD this is 0,
0.
D to
1,
B
1.
you can reach it, correct? This is 1, 1. So this is your adjacency matrix. So this you can represent it like this. This is some A adjacency matrix for you, correct? So let's, for example, I'm just denoting in the A. Okay. Do you know what does A square will denote? If you have this as an adjacency matrix, if you know about the adjacency matrix, if you have A square, what does that mean?
A into A.
So path of
That what?
length.
A
Yeah,
into
that contains
correct.
one output.
So A basically, so whatever A was representing, that was basically was telling you the adjacency matrix wherever you can reach it from a vertices A to B, like any vertices I to J with path length 1. But if you are doing A square now, that will help you to know, you'll calculate this, right? Because this is a 4 cross 4 matrices. It's a 4 cross 4 matrix. And if you are multiplying 4 cross 4 matrix with the 4 cross 4 matrix, what is the value you'll be getting? 4 cross 4 itself, right?
4 square cross 4 square.
Correct. So you'll be getting 4. Okay, let's, for example, if you have 2 cross 3 and 3 cross 2, what should be the matrix multiplication? In which form you'll be getting? What should be the
2 cross 2.
like the 2 cross 2, right? So you'll be removing this, you'll be left with 2 cross 2. Correct? And how do you multiply? The matrix multiplication you are already aware of?
Yeah.
Correct? Yeah. So here you'll be getting 4 cross 4 itself. So now whenever you'll multiply now, you'll be getting a square. Whenever you are multiplying a square you'll be getting, correct? And A square basically will represent you in the adjacency matrix that you have got as A square will tell you how do you reach from I to J with the vertices, with the edges, how many? With the 2 edge length.
2 edges.
Okay. Yeah, let's, for example, for this, we can do it. For A, what was the, we're having we are having 0 1 1 2 0 1 1 0 1 0 0 1. Yeah,
Again
1 0 0 1 and 0 1 1 0. If you multiply this with again 0 1 1 0 1 0 0 0 1 1 0 0 1 and 0 1 1 0. If you multiply this, what will you get? So this is 0 multiplication of 0 1 1
2.
and 0. This will, so 2 means you can write it whenever you are getting more than 1, you can write you can write it 1, and again you can write it here. What should be the value? I guess the 0 0 0 0 0 0, correct? Similarly, I'll be getting 0 0 0 0. Next, I guess 1 you'll be getting, correct? Right. Similarly, if you'll calculate it 1 0 0 0 0. This you are able to know. How do you calculate the matrices? See, basically for the first thing, I'll just tell you the first row and the first column will get multiplied 0 into 0 plus 1 into 1 plus 1 into 1 plus 0 into 0. So this is the first. This is the first. Sorry. First row and first column are multiplied. Okay, so we got it. This is 2. So you can write it 1 here directly. Okay, and again if you'll just multiply it, I guess I'll just multiply it. 2. This will be 1. Again, this is 1 1 1 1 0 1. Okay, did I do any mistake? I guess
0.
I guess this will be 0, right?
Yeah.
Again for the third case will be 0 0 0 0 0 1 1 1. Again for the third case, if you're just getting 1 1, but you can directly write it here 0. Similarly here also it will be 1 0 0 and 1. Now what does this tells you? That similarly if you want to if you want to see, even though you can write it for the transitive closure also. Transitive closure was what? You have a plot, you have been given a graph, okay, and then you have just updating all whatever the graph you were having already, okay. You are just making a transitive closure such that even though in the normal graph you were able to reach it from one place to other place with some 2-3 edges, but in the final graph you are just directly just showing the reachability, okay. Transitive closure will tell you the reachability direct, okay. It will not be telling you how many hopping you'll be doing, but it will just tell you that you can reach it from that place to ith to jth vertices. Okay, this is what your transitive closure will tell you. And matrix multiplication can tell you what's the how do you reach from one place to other place with some particular length like h2. Because you are not dealing with the any weighted thing and all, so you can just get an idea from the a square, aq, a3, a4, a5, like you can just plot it to get an idea. Okay. These are all very simple topics. This won't be most probably be asked in the exam, but yeah, you just have to read it once. Yeah.
So then, why do we sum all possible matrices to find the transitive closure?
Yeah, because that will tell you. See, whenever you calculate that, right? So basically, if you are calculating, right, a square, aq, right? So that tells you that this will be, see, in the transitive closure what we are doing. In the transitive closure, you are just indicating the reachability, right? Correct. So if you are reaching from, let's for example, you were not in the a, so that only that there will be a direct connection, right? In the a square you will be having all the edge in the adjacency matrix, you will be having the all the reachability of 2 length, right? Here it will be for 3 length, 4 length. So similarly you'll just add it to get the final version, right? Correct. So that this final one, whichever the summation, will tell you whether you can reach it or not reach it. This is what the transitive closure also tells you, whether you'll be able to reach it from one vertices to other or not. Doesn't matter how many hopping you are doing. Okay, this is what it will also tell you, right? Got it?
Plus means it is indicating.
Yeah, this is for one length, this is for two length, this is for three length,
So
right? And if you just add it all the things, it will show you adjacency matrix that consists of all the vertices, like from where to where you can reach it, right? Of one length, two length, three length. But whenever you will be denoting after adding this, the original matrix, the final matrices, the final matrix, adjacency matrix will just tell you whether you will be able to reach it from one to C. For example, if you have a vertices, here it is A, B, C, B, C. If in A just A and A square, let's for example in A square, you were able to reach it from A to B. You were able to reach it from A to B with two hopping or two edges. One hop means two edges you were able to reach it. So here it represents one, but here it was zero. Correct? But in the final version, it will show you what 0 plus 1 as 1. That means in the final version, it will tell you that you can reach it from A to B. Doesn't matter how many hopping you'll be doing, but you'll reach it. This is what our transitive closure also tells you, right? Did you get the idea?
yeah, so we add
See, you
the
can see that this plot. See, in this plot, in the transitive closure, you can, so if you will just write it A for this adjacency matrices, for C to D of A, it will be denoting 0, right? Correct? And if you for A, Q, for what it will be showing from C to A, one length, then C to A to D. So for A to D, it will be showing, for A square, it will be showing 1, right? So whenever you'll add those two cases, for A to D, it will be showing 1 for the transitive closure. And from here also, you can see that from C to D, sorry, from C to D, right? For this example, for this graph, for our graph, if you'll if you'll write the adjacency matrix here, to reach it from C to D, what are the matrices that you have? C to D, it will be having 0, correct? But in A square, it will be having C to D as 1. But whenever you'll add both the two adjacency matrix, in the end, you'll be having a matrices that will tell you that you can reach it from C to D directly, like not directly, but C to D is reachable. Okay, this is what it tells you also. Your transitive closure also tells you the same thing. Got it or not?
So C to D is reachable in this graph.
Yeah, this is what in the final also it will be showing you, because you are adding it, right? You are adding it. So basically what basically you are doing, you are just adding it, all those things, whether you can reach it from I to J with one length or two length or three length or four length or n length. You are just adding it all the things in one adjacency matrix, and that adjacency matrix will tell you whether you are able to reach it from I to J. Doesn't matter how many hopping you are doing. Okay. Yeah. So I guess this is done. So this is pretty simple, and this most probably will not be asked in the exam also. Yeah, maximum they can ask you the number of edges that you'll be adding to make it as a transitive closure. Okay, that we have done it. One example that we have done it. Okay, so now let's deal with some of the algorithm to calculate the. Okay, so one more thing. Okay, weighted graph we have to discuss as of now. What do you mean by weighted graph? Can somebody tell me about the weighted graph?
Edges are labeled with some cost.
Yeah, correct. Yeah, so there is some cost attached to it, some weight attached to it, right? So there can be anything. Right? From moving from A to D, it's some cost 4. From C to D, there is some cost 3. Similarly, to reach it from B to C, there is some cost 4. Okay?
Sir?
Yeah.
So can we say weighted graph is a subset of labeled graph?
What is
Because
that
in a
labeled
weighted
graph?
In a weighted graph, we assign a cost of numeric value.
What is
Sometimes
that label graph then?
label graph means I think edge can be labeled with any value.
So then Yeah, then you can directly say that label graph is a sub like weight graph. So both are same only, right? You are just giving the label. That means you are just putting some cost at each age, right? Right. In the label also you are doing the same thing. In the weighted also you are just giving a weight value to the weight like age, right? Yeah. This is nothing. So the same graph that you were dealing with, okay, you just are putting the edge here. Because, and why are we doing it? Because in our normal lives and all, right? So whenever you have to reach it from one state, like this one example, there can be n number of examples, but the one example is if you have to reach it from A to B, okay, and if you are using some train or bike or something, or a flight, let's for example you are just using a flight and you have to go from one city to the other city. Then if you have been, so this edge can denote you the distance, okay, or a cost of going. So let's for example, if you want to buy, if you have to go from city A to B, right, and if from direct flight if you are getting some higher cost, right, and if with the one hopping if you are getting lesser cost, if you have to make the time, not time as a constant but money as a constant, then you can move it, you can use the hopping part, right, you can go it from A to B and then B to C, okay, if you have a money constant you are applying, right? So this can be a one example. Okay, why are we moving toward the weighted age, weighted age graph? See, one example that I was giving you, that see normal graph now there is no cost or nothing weight as such, okay, in the, so there we were able to find so many other things like the longest path to reach, whether we can reach it from here to one path to another path and all, so those things, but there is no cost included, right? We are just telling you to know about the with how many hopping you will be able to cross it, how many hopping means how many edges will be crossing it, right? But now we'll be dealing with all the things in the graph, we'll be just dealing with the weighted graph where we'll be allowed to, we'll be having a cost also, we'll be having cost or you can say the like, what do you call that? Yeah, so basically it's like I'll just give you one example here for a weighted graph. So this was the same simple example. Here also you can give you, let for example, this you have Pune and then you have a Bombay, Chennai, Delhi. Okay. So let's for example, there is some flight from Pune to Delhi and then Delhi to Chennai and then from Chennai to Bombay to Chennai is also available. And then from Pune to Chennai also available, right? So weighted graph means like, let's for example, the time it was taking from P to C was 1 hour only, but here it will be taking 2 hours and then it will be taking some again 2 hours. Okay. So if somebody has a time constant, then it will be taking from Patna, that Pune to Chennai direct flight. But if somebody has a cost constant, okay, let's for example, this cost constant, the weighted graph, and the other plot that I can tell you is the cost price. So let's for example, here it was costing some 10K and then here it was like 7 and then it was 2K. So if somebody has a price constant, then it can use the this as a hop, like this as a path, right? So see, this weighted graph, it's like pretty simple. You're just putting some cost effective, you're just putting some cost, okay, on reaching from A to B or whatever the vertices that has been given to you. This is the one application, and I'm saying you again and again, but this can have a n number of application in the in the normal life also. See, okay. So that's why in the weighted graph we'll just deal with some of the algorithms, some of the 2 3 algorithms that will just tell you to solve your time constant issue or the price constant issue. Okay, so what's the minimum cost or the what's the minimum time it will be taking if I have to reach it from here to here. We're just booking some tickets and all, it will be giving you the minimum. If you are just putting the time constant or the price constant, it will be giving as a similar final solution to you, right? So, so these are some of the application that basically the weighted graph in our normal life. Okay, and if you have to solve those type of problems, wherever you have a problem of the graph theory, okay, with the weighted graph, and then you have to put some time constant or the price constant, okay, or the range constant, whatever you want to call that, then there are some 2 3 algorithms that will help you. That 2 3 algorithm that we are studying here, Dijkstra algorithm or the Bellman-Ford or the Warcel methods that we are dealing with, to just calculate the shortest path with putting some of the constant. Okay, if you are putting the time constant, or the price constraint, whatever we are putting it. Okay. So we'll see that how do you solve with the help of Dijkstra algorithm. I'll just start with one example, but maybe that will help you to understand it nicely. So, okay, and in the weighted graph also, right? In the weighted graph also, you can have a negative value also, you can have a negative cycle also. And you will see that for a negative value or for a negative cycle, which algorithm we use it to calculate the shortest path. Okay, and if you have a positive values all together, all positive value in the weighted graph will be having a which algorithm basically you use it to calculate the shortest path in those plots, right?
So,
Yeah.
if there is a native cycle, then shortest path is not.
Yeah, so yeah, there is some application. I'll tell you. So I'll just write it down. The 2-3 things that you have to remember it, or you should be knowing that. The first thing is if you have to calculate. So for a weighted graph, we'll be just dealing with how do you calculate the shortest path. Okay. Let's for example, if you have to calculate it from some fixed weight, fixed what you have fixed the vertex. Okay, and then you have to calculate the from this fixed vertex you have to calculate the basically you have to calculate the shortest path from this fixed vertex to the all the other vertices. Okay, and if you have and there is no negative weights attached, then you can use it. Even though you can use the Bellman-Ford also for this, but mostly you'll be using the Dijkstra algorithm because of the time constant. Okay, so we'll be using the Dijkstra algorithm for all those cases wherever we have a weighted graph has been given to you, and then you have to calculate the fixed path. You have to calculate the shortest path from some fixed vertices to each of the other vertices that has been available in your graph. Okay, then you will be using the Dijkstra algorithm. Okay, the next time the thing is if you have been the vertex has been fixed to you have to calculate the shortest path from that fixed vertex to the other vertices, but you can have a negative weight. Okay, so you have a fixed path, fixed vertex, but the problem here is you have a negative weight.
So, what is the fixed vertex?
Yeah, see, you can have a example, right? So let's for example you have a given example. So you have to this A, B, C. Okay, if you have to calculate the shortest path from A, this A I have fixed it, right? From A to B and then B to C. So sorry, A to C. Okay, I have to calculate it. Let's for example this 20 minutes it takes 10 minutes, and this is 40 minutes, right? So I'm just fixing A. So can you tell me the if you have to what is the shortest path from A to B and how much time it will take you? 20, right? A to B. Okay, and if you have to reach it from A to C, so this is fixed, right? So from I have to calculate it from A to B, similarly from A to C. So here you can use the Dijkstra algorithm, right? We are just fixing A and then we are calculating from A to each of the other vertices the shortest path. Is it clear to you? Is it clear?
Yes, sir.
Yeah. So similarly, for the if you have a weighted plot, if you have a weighted graph, and in that weighted graph, some of the weights are negative. Okay, so if some of the weights are negative, you will see that the Dijkstra algorithm will not work there. Okay, so there we'll be using the Bellman-Ford. And the other thing is what? What is the other constraint that should not be there? It should not form negative cycle.
Negative cycles.
Okay. Do you know what is that negative cycle? If you have a plot A, B, C, this is from A to B, B to C, and this is let's for example this is 20, this is 10. Which of the following is a negative cycle?
Second one.
What?
No one, sir. No cycle.
No cycle.
No one, yes.
Now tell me. The second one is negative cycle, having a negative cycle, right?
Yes, sir.
See, and this is having a negative weight. Okay, so if you'll see the summation, it will not be a negative value, but here it will see, you will see that 10 plus 5 minus 16, that is basically a negative value, right? So that's why you'll call it as a negative cycle. That should not be occurring. Okay, for a Bellman, for if you have to apply the Bellman for an algorithm, you should not be having a negative cycle. Okay, that should be there in your mind. If you have a negative cycle, you'll not be able to apply any of the algorithm. At least the 3 algorithms that we are using, you'll not be able to apply. So the third thing is, you have to calculate the shortest path from A to B. Like you're just fixing both the vertices. Now you have fixing both the vertices, fixed vertex. So from any fixed vertex to other fixed vertex. Okay. Here also negative weight is allowed, but negative cycle is not allowed. Here also, which algorithm will be using? The Warshall algorithm, you can use it. Here we are using the Bellman. We'll deal with the Dijkstra algorithm today. Let's start with the, so here in the Dijkstra algorithm, you have been given a graph. Okay, you have been given a graph that can be a weighted. Okay, so that is a weighted graph has been given to you. Now you have to calculate from one particular vertices, what is the minimum distance, what is the minimum shortest path that you have to cover, shortest path from that vertices, that fixed vertices, to each and every other vertices that has been given in your plot. Okay, see, Dijkstra is very simple. It's like there's nothing in the Dijkstra algorithm, right? This is pretty simple. Whenever, so this is just a if and one simple if and else condition. If there's, for example, if for whatever you're starting with, so if you are starting with du, okay, and then you have a weight in between, you have a weight sum, and if that weight is less than wherever you are reaching, if that is less than that, then you will just update the value of dv. Okay, see, let's, for example, it's a pretty simple example. If you have a, if you have a b, if you have a c, correct, and if you have to go from here to 2, this is 2, this is 1, and this is 4. What did I say? If you have to start it, so you have to start it from here. If you have to start it from here, what did I say? So this will be your du. Okay, now see that a to b, first of all, we'll start with a to u. So a to b. So the first thing is you have to, so what did I say? In the Dijkstra algorithm, you have to fix one vertices and you have to find the shortest path to each of the other vertices, right? So now let's, for example, one more thing, you will initialize the value as infinite. So you'll just take it as, in the starting, you'll just think that, yeah, so whatever the professor was saying, sir was dealing with one example that you have to, a fire has been started from A, and then how much time it will take to reach each of the other vertices, like all the vertices has been connected to some pipeline with the oil pipeline. Okay, and then how much time it will be taking, taking it to reach it to each of the other vertices, right? So here also you can just think in that way. So Dijkstra is very simple. So if this is a pretty simple if and else condition itself. So you start with du, right? So you can think of A as a vertices that you have to start with du, correct? And then the next thing is what? B, right? So this you can think of as a dv, right? Yep. In the starting, what did I say? You have to think as this to reach the fire at B, it takes infinite times. Here also it is infinite times. So each of the apart from A, you can just initialize the value as a infinite. So it takes infinite time to reach B from A and to C also, right? Now the next thing is this if and else condition you have to apply. So what is that if and else condition? I told you du plus this weight, whatever the weight has been given, is less than dv, then you can directly update the value as dv equals to du plus weight. Correct? So what is the value of du here?
0.
0, right?
0.
So here it is 0 because you are starting with A itself, right? So that's why. What is the weight given here? 2, right? Correct? And what is the dv?
Infinite.
Right, infinite. Is this holding? Is this our condition, if condition holding?
Yes.
Yeah, so it is holding. That means we'll update the value of dv, right? So dv will update it. dv equals to 0 plus 2. That means 2. So it will take some 2 minutes. So if that, for example, this unit of minute only. So it will take 2 minutes only to go to reach this fire to B, right? So from A to B, you can see that the shortest path is what? A to B, and the time that is taking is 2, right? Now you can think of as A to C, right? You can think of as A to C. How will you start with A to C? How will you do that? So now you have the values, right? You have the values of dv. Now you have a value of dv as what?
2.
2, correct?
2.
Yeah, 2 is there. So now you can think of as now let's start with b2. Like if you can think of as see, the best part is you can deal with that. See, A is been given here, B and C is already given. So in the first step, what did you do? You started with A, right? So you started with A, 0, infinite was given here, right? Next step is you already know that from A to B, is there any direct connection? Yeah, there was a direct connection and you took some 2 minutes to reach there. Is there any direct connection from A to C? No, right? So it was infinite only. So in the first step, you just fix the value of 2, right? So now A, B come here, B came here directly. So now you can use the value. See, if you have to, in the next step, you have fixed the value A to B. It will take 2 minutes. 2 minutes or whatever the unit that you have. The shortest path from A to B is 2. That is the weight of the cost for reaching A to B. Now for C, you can see that from C, what is that value? Infinite, right? From A, you can't reach C directly. You can reach it, right? You can reach it basically
Yeah,
A to reach. What is the value?
Yeah, 4.
Yeah, 4 has been given to you.
Yeah.
Okay, so why did I? Yeah, so you can write it here 4. So from this 2 or 4, whatever is the minimum, you just take out that one. So the first step, you have taken out the 4 here. Now, in the next step, 2 is fixed, right? For you, A to B, 2 is fixed, correct? Now 2 is fixed. Now, can you reach A to C via B? Because B, now you can use the B. Can you reach it from A to B? Like, can you reach it to C from A to C via B?
Yes.
Yes, sir.
What is the minimum cost?
2 plus 1, 3.
2 plus 1, 3, right? So 3. Now you can see that 3 is like the minimum. So after this 2, 3 is the minimum, right? So 3 came here. So A, B, C now they are done. So A to C, you can reach it with 3 as a shortest unit. See, if this is not clear, I'll just give you one bigger example. So maybe that will clarify everything. So let's, for example, this is a
So we have to calculate for every edges given between the vertices.
Correct.
Right.
From if you're starting with one, yeah, correct. So let's start. I'll just give you one example that will clarify.
So it is like somewhat BFS process. It just goes parallelly. So first we calculate for direct edges, then 1 hop, then 2 hop. Is it?
Correct. So in the DFS also DFS is like a little bit different from this. DFS, you don't have any ages, like you don't have any weights for those cases. You just calculate.
Yeah. Only counting is there.
Yeah, correct. The counting. Okay. So let's, for example, you have given the ages for all the other cases. Now, let's, for example, the source, I have to start from A. I have to start from this. This is our source. I have to start with 1. Now I have to reach each of the other vertices, right? I have to use the Dijkstra algorithm. I have to reach each of the other vertices. How will I reach? Now you can just build one this. So you have to reach it from 1. No, 1 more. This is 2, 3, 4, 5, 6. Correct? Now let's start this. In the first thing, what did I do? You have to just search from where you can directly reach. Okay, and what is the weight for that case? So from 1, which of the vertices you can directly reach from 1? Can you reach it to 2?
Yes.
Yeah, you can reach it to 2, right? So what is the weight for that? So the first step is to 0, infinite, you can put it. So it started with infinite. The second step is the first. If you have to reach it to 2, you'll take 7 units, right? 1 to 3, is there any connection to 1 to 3? Right, 9. 1 to 4, is there any connection?
No.
1 to 4, no. So it will
No.
be infinite only because it will take infinite time. You can just think of as an infinite it is taking. 1 to 5 also there is no connection directly, so infinite you will think of. 1 to 6 also, this is 14. So which of the following is the minimum? So this is the minimum, right? So now you can reach it from 1 to 2 with 7 unit, right? So 7 is fixed now. So now in the next case, you can use the 1. So you can go via 1 to reach each of the other places. Now, can you get any other like any other weight in spite of 9? Any other weight that is less than or via using 1 to 4? If you have to reach C, now you can use 2 also. The 2 vertices also you can use it. Now you have to use 1 and 2 and then reach it to 3, 4, 5, 6. Can you reach it to 3? So if you will use it
Yes.
2 also, but you'll be having 7 plus 10, that is 17, but that is higher.
Yes.
So that's why you'll be using 9 only, correct? If you have to reach it to 4, how will you reach to 4? You can reach it to 4. Yeah, this you can reach it 15
7
plus 7.
15.
22, correct? How can you reach it to 5? You can't reach it to 5. So that's why it will be infinite only. Can you reach it to 6? Yeah, 6 is there, 14. Which of them is minimum? After 7, you have a minimum as a 3, right? So now you can reach it from 1 to 3 also, right? 1 to 3. That means you can reach it from 1 to 2 with 7 unit as a minimum distance. Similarly, minimum weight, whatever you want to call that as. 1 to 3, you can reach it with 9 as a minimum unit. So whatever the unit you can. Now you can use it 2, 3 also. Now you have to reach it from 1 to 3 to 4, 5, 6. So 7 is fixed, 9 is fixed. Now can you reach it to 4 by 2 and 3?
Yes.
Okay. What is the length?
But 28. Oh, that is more than 22.
Okay, that is more than that. So 22 will be fixed. Correct? Can you reach it to 5 using 1, 2, 3?
No.
Okay. Can you reach it to 4? Okay, 1, 4. How are you reaching? That is 1, 2.
1, 2, 3,
No.
4.
We can go it by this, right? We can use this 9 plus 11. That will be 20, right? 20. Correct? So we can have a 20.
Can be, yeah. It is not necessary to use both the edges.
Which, no. You can use it 1 or 2. You just have to, the next thing is, you can use 2 or 3.
Yeah, 2 or 3.
So you have to start from 1, you have to reach it to 4. You can use 2 or 3 in between. So here you are using 3. So now the 20 is there. You can get it 20, right?
20
if you have to reach it to 5, what is the infinite only? You can't reach it to 5 using 2 and 3, right? Similarly for 14, what is the value? 14. Okay, how will you reach to 6? Okay, let's, for example, this is 2.
Yeah, 1, 3, 6.
No, if you have to reach it to 6, you can reach it directly by 1, 3, and 6, right? So 9 plus 2 is 11. Correct? So now, which of them is minimum? 11 is minimum. Now you can take it 6 here. So 1, 2, 3, 6 you have taken, right? So now you can use 2, 3, 6 to reach it to 4, 5. So 7 is done, 9 is done, can you reach it to 4 using 236? Four, I guess the 20 only. This will be 20 only. You can reach it via 1, 3, and 4. That is 20 itself. Now 5, can you reach it to 5? I guess 5 also you can reach it. Now, if you are using 6, right? So if you are using 6, you can go it like this, right?
Yeah, 20.
And we can go to 1, 2, 1, 3, 6, 5, 4. Sir.
What? Can you repeat that?
1, 3, 6, 5, 4.
Correct. 1, 3, 6, 5. Yeah, this is smaller. So 9 plus 2 is 11 plus 9 is 20. So I guess 20. Correct? I don't think so. There's anything lesser than that. Yeah, and if you have to reach it to 6, so this is already been done. Okay. So the next thing is this. Both are 20, right? Both are 20, right? So you can take it any of the two. You can take any of the two. Okay. If you are just taking any of the two, so you can just take. Let's for example, you are just taking 4 here. After 6, you can take 4 here. So now the same thing. You are done with this, and then now you can use it 2, 3, 6, 4, all the things to just reach it to 5. Can you reach it to 5? Yeah, you can reach it to 5 with 20 units only. So now 20 is also done. So that's thing. So now you get the length for each of the cases. If you have to go from 1 to 2, 7 is the minimum. 1 to 3, 9 is the minimum. 1 to 6, 20 is the minimum. Similarly, 1 to 5, 20 is the minimum. 1 to 6, 11 is the minimum. This is how you use the Dijkstra algorithm. Is this clear to everyone, or should I repeat it?
No, sir, clear.
Is this clear to everyone?
Yes, sir.
Okay. So we just have. So from the starting, I'll just give you a brief whatever we have discussed today. We have started with topological sorting. Okay. We have started with DAG. Okay. So directed acyclic graph we have started. Okay. And then we have discussed about the topological sorting. How do we do that? How do you write the topological sequence? Then we have dealt with how do you calculate the longest path in a DAG. Okay. Directed acyclic graph. How do you find the longest path? Okay. Then we have calculated how, when we have discussed about the transitive closure, that is also pretty simple. How do you convert a simple graph to a transitive closure? Okay, that will tell you the reachability from each other. That doesn't tell you about the hopping, but that will tell you the direct how reachability. And then we have discussed about the matrix multiplication, and then we have started with how to calculate the shortest path in a weighted graph. So weighted graph we have discussed, simple, it's very simple. Then in the shortest path we have just discussed about the Dijkstra algorithm. Okay. In the next meeting, whenever we will meet, we'll discuss about the Bellman-Ford and the Warsaw method, and then we'll discuss about the minimum cost spanning tree. Okay, is this clear to everyone? I can just share this file. If you want, I can just share this file.
Yes, sir, please.
Yes.
Yeah. Okay. So that I'll say that will be there in the portal. I'll upload it there. Is this clear to everyone?
Yes, sir.
Okay. Okay. Okay, then if you it is, then we'll meet, I guess, on the Tuesday again we'll meet and we'll try to finish it off, and then we'll try to solve some problems also. Okay.
Yeah, okay.
Whatever we have discussed, if you have any doubt, you can just ask me. Otherwise, I'll just drop off. Thanks for coming, and we'll discuss more examples in the next meeting. That is, I guess, on the Tuesday, 8 to 10. Okay.
Yes. So,
yeah, I'll
where can I find it? PDF?
Yeah, this PDF you'll be finding it on the supplementary content. I'll upload it by Monday. You'll be getting it there. Not Monday. Yeah, Monday you'll be getting it. By tomorrow it will be getting it.
Okay.
Okay. Thanks everyone for joining the session, and then have a good night.
Thank you, sir.
Thank you,
Have a
sir.
good dinner, and then okay. Thanks everyone.
Thank you, sir.
Thank you.